Welcome back, everyone. This is Mr. Havenhill here to present to you day 2 of Volumes by Revolution. And just to recap what we've done so far, what we did last class is we said, hey, what would it look like if we were to take the area under a curve, in this case the square root of x, from A to B, and let's revolve it around an axis, in this case the x-axis. Let's go ahead and let's do so. And then the question is now, what would be the volume of that particular solid? Well, it turns out that we can find that fairly easily. And what I'm going to do is backtrack a moment and start with a very basic idea. Suppose we were to take this area and we were to take an arbitrary rectangle, anywhere inside this particular interval, and then revolve that one rectangle around the x-axis. Now I can easily find the area of this cross-section, and then its thickness. If I multiply area by thickness, I actually get volume. I can find the volume of that particular cross-section right there, and then what I can do is add up a bunch of volumes and get a very crude approximation for the total volume that is of this solid that's created by revolving this area around the x-axis. Now, if I were to increase the number of rectangles from 5 to say 10, we see that our approximation is going to get better, and it's getting much better. And if we increase the number of rectangles to say 30, it's going to be even better. And if we were to increase the number of rectangles to 100, you'll notice that my rectangle is getting thinner and thinner. The area of the circle is still going to be the same, but my thickness is getting thinner and thinner. And as I add up all of those disks, my approximation is getting closer and closer and closer to the actual volume, the exact volume. And so the idea here is that when we're trying to find the volume of revolution, our strategy is to say that the total volume is equal to the sum of individual volumes, a volume of a cross-section. In this case, it's area times the thickness. And this is applicable to cross-sections that are perpendicular to the x-axis or cross-sections that are perpendicular to the y-axis. So I have a question for you now. This has been our strategy so far, and it works pretty well. But I have a new question. What will happen to this strategy if we revolve about something that is different than the x or the y-axis? Will our strategy change? So let's go ahead and let's see what happens. Let's take the same square root function here and let us move the axis of revolution so that it's at x, or at y equals -2, and let's revolve this area underneath the curve of the square root of x from A to B, and let's revolve that entire area about this axis of revolution. Now, let's go ahead and let's see what that looks like. What we see here is a much bigger shape that appears to have a big cylindrical hole drilled right through the middle of it. And the question is still remaining. How would we try to attack this question if we were to try to find the volume of that particular solid? Well, I believe that the strategy is still going to be the same. if we were to take a cross section right down the middle of this particular, take a slice right down the middle of this, we would find ourselves not with the washer anymore, I'm sorry, not with the disc anymore, but with a washer. And I maintain that the strategy is still going to be the same. Can we find the area of that washer and then find its volume, which is going to be its area times its very, very small thickness, and then take the sum of all of those individual little volumes and find the total volume by doing so. And as we see here, we can sweep a washer across this entire interval from A to B, and what we see here is this shape maintained throughout the entire length of the interval from A to B. And so the question again comes back to what will happen to our strategy if we revolve around something different than the X or Y axis, and it looks like our strategy is still going to be the same. Nothing is going to be different. We're still going to try to find the area of a cross section. It's just slightly more complicated. So let's go ahead and let me show you kind of what we're looking at here. This right here represents the area of a particular cross section of a washer. And suppose I wanted you to find the area of this pink shaded region. Well, how would we find the area of that pink shaded region? Well, hopefully you would say, well, Mr. Havenhill, that's not too complicated. That's going to be the area of the big circle minus the area of the smaller circle. And that's easy to find. The area of the big circle would be pi times the bigger radius squared, our outer, and we would subtract from that the radius, the area of the inner circle, which would be pi times the radius of the inner circle squared. And so what we have here is the following. The strategy is still to say that the volume is equal to the integral of the area times the thickness. Where in this case, the area is just a little more complicated. Let's suppose that we're taking a vertical. That's pretty terrible. Let's fix that one. Let's suppose we're wanting to find a vertical. Wrong tool. A vertical washer, and I wanted to find the area of the big one minus the area of the small one. This isn't cooperating. There we go. So hopefully what you would tell me would be, well, Mr. Havenhill, this isn't too complicated. This is going to be still pi times big R squared minus pi times little r squared. That would be the area of one particular cross section. And then since this is a vertical cross section and the thickness is a function of x, our volume is still going to be the integral of the area times the thickness. We just have a slightly more complicated integrand. So let's go ahead and let's take a look at this particular function, and let's see if we can try to describe the actual area of a particular cross section. Let's see if we can actually figure it out analytically. Now I've gone ahead and I've taken a screen capture, and we'll go ahead and we'll head on over to the Windows world. Okay, so we've got ourselves a screen capture here of this entire volume. And what I want to do is I want to try to describe the area of this particular cross section. And so what I've got here is clearly a radius that's a little bit bigger than just simply f of x. The radius is clearly more than just f of x, because this right here is f of x. What else would contribute to this particular radius? Well, we've got not only just f of x, but we've got this additional chunk right here. And what is the length of this chunk? It's 2. So the entire radius of the outer circle is actually going to be f of x plus 2. And so this would be the radius of the outer. What would be the radius of the inner circle? Well, the radius of this piece right here is just simply 2. What I'm going to set out to do now is to try to describe analytically the formula for volume of this particular shape. So the volume is going to be the integral of the area of my cross section, which is going to be pi r squared. Now I'm going to go ahead and pull the pi out. And so that's going to be f of x plus 2 squared minus the area of my inner circle, which is going to be pi little r squared. With your permission, I'll just go ahead and put 4 dx. And then what we'll set out to do is to try to describe this a little more analytically. So instead of writing f of x, my actual function was the square root of x. So we've got the square root of x plus 2 squared minus 4 dx. And then from here, we would actually multiply this all out. We can use your favorite 4-letter F word and FOIL all that out. Careful where your mind goes there, folks. We could FOIL that out. We can use boxes, just expand it, basically, and then solve that particular integral. It's really, honestly, it's not too tough. The hardest part of this problem is trying to figure out how to set up the area for a particular cross section. All right, ladies and gentlemen, let's try to do something a little more challenging. Let's take the function f of x is equal to 9 minus x squared all over the interval from 0 to 3, and also the line y equals 12. And what I want to do is take the area that's in between these curves. Now this is not going to be drawn to scale, so for those of you with OCD, you'll have to get over it. And here's 12. So what we have is this area here and what we're going to do is revolve this area about the line y equals 15. Now some of you might be thinking to yourselves, what? Wait, 15, isn't that above our particular graph? It is. Revolve about y equals 15. And so this is what we're looking at here. And this is going to get a little complicated because our shape exaggerate the oval here a little bit. Our shape is going to have a big hole right through the middle of it, but our region this time it's just a little weirder. So if I'm wanting to find the volume of that solid, will my strategy change? Whoops, come back here. And I maintain that the strategy is still the same. Now, sorry that this doesn't fit quite perfectly. The difference here is we are not allowed to think robotically. We have to think very creatively in terms of trying to still take a cross-section right through the middle of that and try to determine the area of that particular cross-section. Now, this time it's a little different. The area of our cross-section, it's still a washer, and its thickness is still a function of x, and so the strategy is going to still be the integral of our area times the thickness. That strategy is the same, but the description of this particular area is a little different. And so whenever we do these kinds of problems, we really have to put on our thinking cap and we have to ask ourselves, okay, how can I analytically describe the area of the cross-section that I'm looking for? Because it's not always going to be the same. Each question is different. And as we'll soon see, there are definitely patterns that emerge that will make our life a little bit easier. But we can't afford to allow ourselves to do any robotic thinking. And so with that said, let's go ahead and let's describe what the radius of the outer circle in this case would be. Let me get a better line here. The radius of this particular washer, for the outer radius, is going to actually be, this time, 15 minus the parabolic curve here. 15 minus 9 minus x squared. This length right here is 15 minus all of this junk in the trunk down below. And then the radius of my inner circle, well, that one is just simply going to be 3. So this appears to be 6 plus. So when I reduce this, or simplify this, I'm sorry, this appears to be 6 plus x squared when I simplify this algebraically. So my volume in this case is going to be the integral, and since these are perpendicular to the x-axis, my limits of integration are going to be from 0 to 3, and then I'm going to have pi times my outer radius squared, so 6 plus x squared minus pi times the inner radius squared, so 3 squared. So then my volume is going to be pi, I have a common pi I can pull out, from 0 to 3 of 6 plus x squared minus 9 dx. And I can expand all of that and algebraically, and that's pretty trivial. I would end up with the volume is equal to pi times from 0 to 3 of 36 plus 12x squared plus x to the fourth minus 9, all of this times dx, and that ends up becoming pi times what is that? 26, or sorry, 36 minus 9 is 27. Integrate that, get 27x plus 4x cubed. That looks like that might be x to the fifth over 5. And that's going to go from 0 to 3. And when I simplify all that mess, I end up with 1,188 over 5 pi. And so the mechanics from this point forward, that's all stuff that we've been doing for a while now, for several months. We can do this easily. The hardest part of this particular problem, in my opinion, is setting up this piece right here and setting it up accurately and trying to figure out, okay, how do I represent the area of my cross section? That's the trickiest part of all of these problems, and the trickiest part is not thinking robotically, but rather trying to treat these individually and really trying to scratch your head and say, all right, how do I algebraically describe, if I'll come over here and for dramatic effect I'll zoom in on the piece that I'm looking for. How do I describe the area of any one of these cross sections? And so what we'll find out is it really depends where the axis of revolution is. Is it above our function? Is it below our function? It does kind of make a little bit of a difference in terms of how we initially set it up. And so, and as I mentioned, after we've done a few of these, some patterns are going to start to emerge, and you're going to notice some ways of simplifying these even faster. But I don't want to spoil all the fun. I'll let you kind of discover some of those things. I don't want to steal all the fun for you guys. So what I'd like to do is one more example for you guys, just to kind of show you what it looks like. In fact, you know what we'll do is we'll take the same we'll take the same function. This time we'll let f of x is equal to 9 minus x squared. We'll take this guy and we'll use it again. And what I'm going to do is we're going to take over the same interval from 0 to 3. Again, those of you with OCD, sorry, this is not going to be drawn to scale. And I'm going to take the area under the curve this time. And what I would like to do is revolve it about the line x equals -2. That means we're now going to be spinning our shape in this direction. And so we're going to be rotating it horizontally rather than vertically. And it looks like we should have gone a little bit further over that direction. Sorry about that, y'all. And so now what we want to try to do is figure out the area of a cross section. These can be a little tricky to draw, especially if you're using a tablet. And as I've been trying to really allude to over and over and over again, at the risk of sounding like a broken record, the volume is going to still be the integral of individual volumes. Actually, that does look kind of butchered. I'm really sorry about that, y'all. This should be over a few extra lines here. I'm sorry that's going to be driving some of you crazy. Yeah, sorry about that. So the idea still can be, can we take the area of a cross-section and multiply by its thickness, which in this case is going to be dy, and then add up all of those volumes to get the total volume of this solid of revolution. So this time we're going to be dealing with functions of y as opposed to x. And the volume is still going to be the area of that cross-section, which is a washer, and it's still going to be the integral of r outer minus r inner squared, r outer squared minus r inner squared, dy. And I just want to make a quick point because I see this happen all the time. Ladies and gentlemen, a squared minus b squared is not the same as a minus b squared. Please don't make that silly algebraic mistake. I see it all the time when students are trying to compute these bad boys, and that's just silliness there. So just please avoid that. So in this particular case, we need to try to figure out how to describe this algebraically. And so my r outer in this case, well, what is that going to be? We've got y is equal to 9 minus x squared. With your permission, I'd like to make this x squared is equal to 9 minus y. And what I've done is I replaced f of x with y. And then what I'm going to do is say that x is equal to the square root of 9 minus y. Now, technically speaking, this would be plus or minus the square root of 9 minus y, but when I look here, I'm not wanting the negative version. I only want the positive version of what I'm seeking to solve for here. So this is the only one I'm looking for. And so I claim that the radius of the outer circle is going to be my function plus this extra little chunk, which I believe was 2. This length is 2. Yes, it's at x equals negative 2, but this length is my function plus an additional 2. And so my r outer is going to be, the radius of my outer circle is going to be the square root of 9 minus y plus 2. And then r inner is going to simply be 2. So my volume in this case is going to be pi times r outer squared, which is going to be the square root of 9 minus 2 plus 2 squared, minus the inner one squared, which is 4 dy. And then we need to figure out my limits of integration. And we're going to be going, since we're focused now on the y-axis, we're going to be traveling from 0 to 9. And then we compute that integral. And we do some fancy algebra, and we do some antiderivatives, we expand some things, and we end up with the volume is equal to 225 over 2 times pi. But once again, the strategy is the same. It's the volume is equal to my area times my thickness, and when I try to describe the area of my washer, whether it's horizontal or vertical, it's still going to be r outer minus r inner, and or the area of the outer minus the area of the inner. And so let's go ahead and let's summarize this in writing. All right, folks, I just realized for a brief moment some of you are about to have a heart attack. This right here should not have been 9 minus 2. It should have been 9 minus y. And then when we do all the algebra, we end up with that particular statement. I do apologize for any unnecessary anxiety that was caused by that particular little mental lapse. Sorry about that. Okay, so let's summarize all these points, and to my sub, I'm going to invite you to hit pause wherever need be to let students write this down. So to summarize, the first thing is sketch these graphs so we can visualize what we're working with, especially so you can visualize the cross sections. If your disk is perpendicular to the axis of revolution, then the volume is going to be pi times radius squared dx, or volume is going to be equal to pi times the integral of radius squared dy. The orientation of the disk is going to determine which of these you choose. Now, what happens are when we start to revolve around a different axis than simply the x or y axis, that is where we start to get something a little more complicated. We end up with the washer. And so if our cross section is a washer, then the volume is going to be pi times the integral of the outer disk minus the area of the inner disk dx, or volume is going to be pi times the integral of the area of the outer disk minus the area of the inner disk dy. And again, which one of these we choose is going to be dependent upon the orientation of my washer. If I have a vertical washer, I'm going to be dealing with this top relationship here. My thickness is a function of x. If I'm dealing with a horizontal washer, then I'm going to definitely utilize the second representation here, because my thickness will be a function of y. If you rotate about a line y equals c, then the following may be helpful. It could be useful as a guide. If your function is, if f of x is greater than or equal to g of x, which is greater than or equal to c, then the following may be useful. Our outer could be represented as f of x minus c, and your inner radius could be represented as g of x minus c. Again, these are guidelines. Ultimately, what you need to do is draw it out and try to analytically describe what you're seeing here. But this could be a very useful guide for you. And if c is greater than either one of your functions, where c is on top of your greatest function, then our outer might be c minus f of x, and our inner might be c minus g of x. Again, these are just a guide. You want to describe it algebraically, ultimately, to see what's going to work as you try to describe the area of your washers. Lastly, big R squared minus little r squared does not equal big R minus little r squared. That relationship is silly. So what I'm going to invite you all to do is to work on, from Larson's 9th edition, it's on my site, page 465. I'm going to ask you guys to work on these odd problems. Use Calc Chat to check the solutions. And then once you're confident, I'm going to ask you to give numbers 12, 14, and 16 a try. Thank you guys so much for your time, and good luck.